this nozzle is at a higher pressure than the ambient. Okay, so what we have done here is this. Let me go from the settings. So basically, you have to first create a mesh. I think most of you are aware of the procedure. So once you have a mesh, you open that mesh in Fluent or whatever software you are working on. Then I will just go through the setup quickly. So that let me choose. Yeah. Okay. So this is the general. You can go on full screen and see because there's some small text which will be visible. I don't know if you are able to see, but anyway, I will record this. So if you go to the setup, so general, it is a density based solver. You can take absolute velocity formation, and this is a planar. You can do steady and transient both. Sometimes steady is little bit tricky to stabilize, so transience is much. It is better in terms of stability. So you can use generally the cases are steady, but if it is a turbulent case, then transient is what you should do. Try with that. Try with steady if it works. Otherwise, you can go to transient. Fine. So mesh, I think you all can scale and check. This is the mesh. Now let us go to model settings. So what models are there? Energy model has switched on. Okay, because your air will get compressed, density will change, it will get cooled. All sort of temperature changes are there. So it is required to have energy model to be on. Okay, this I'm talking about Fluent. I am not sure about the settings in CFX or console if someone is doing. So Fluent, again I will, yeah, I think it is written on top. So energy is on. Viscous, you can use any what do you call turbulent model. Here I have used a KF Sorum, which is a standard model, realizable KF Sorum with standard wall function. That's all. So when if you are trying to replicate this case, you can just open that viscous panel. It will a pop-up window will open, and then you can use the settings. Okay. Anyway, this is getting recorded, so you can go through it again if you want. Then the radiation is not required, no heat exchanger, everything else is off. So the only change you have to do here is switch on the energy and the turbulence model. Okay. Then go to materials. So this is important here. Solid, we don't do anything. Solid is for walls. So we are not interested in any heat transfer or heating or cooling of this. Basically, you are interested in the fluid medium. So fluid medium, you will say air is a fluid. So let all the default properties be there. Don't do any change there. Only thing what we need to change is density, ideal gas. Okay, generally by default the density is constant. That you change to ideal gas, or if you want to do some real gas, that is also fine. But this one, what I did, it works. So just to keep it simple, just go with ideal gas density. So what it means is that density will not be constant and it will vary. That is what is the most important criteria or requirement for compressible flow, right? If your density is constant, it will not be compressible flow. Then CP and other things you can keep it constant, and you may vary. That I'm leaving up to you. But generally, this constant, keeping other properties constant is sort of okay. We are not much concerned with that. Basically, we are just trying to see here the effects of density or compressibility. Okay, so this is what you should you must remember to do before your starting case. Change the material properties. Then cell zone, nothing to be done here. Go to boundary conditions. So there are a lot of, there is one inlet. Okay, you can define a velocity inlet. This is basically a pressure inlet. So you can that is one of the recommended types based on what geometry or what problem you are working on. So, for example, people who are working on bluff body, you could have a velocity inlet. You can specify Mach number or velocity of the incoming flow. Okay, so this is how we have defined for this particular case. So this is a pressure inlet. You can see and we have given some pressure. So this is approximately 5 bar. So what we are trying to say here is that this is the pressure inlet, this particular boundary. Okay. So what we are trying to simulate is that, let us say this is connected to a tank which is at 5 bar pressure. So as I told, for under expanded jet, this anyway we have to explore again. Under expanded jet, pressure ratio is important. What is the ratio of your ambient pressure and nozzle pressure? So now nozzle is at, this is 5 bar pressure, and just keep the same here and keep it constant. This pressure is not varying. And then you can direction of specification is normal. This is normal to the boundary. So I'll just say normal to the boundary. This pressure is increasing. Turbulence, you can to be simple, you can see intensity and viscosity ratio. These are the default values. So I've not made any change here. Thermal, you can give a total temperature of 300 or 400, whatever case or details you are trying to simulate, that you can fix. So this is how you specify the boundary conditions, and let us not talk about outlet will be. So there are two outlets which I am keeping as pressure outlet. Okay, if you could see here. So where are these outlets located? So here the case is that these two are parallel walls, and in between one wall there is a hole where this nozzle is fixed, and far from that we have a pressure outlet. This is the pressure outlet. Okay, this will again, it will be decided on what geometry and what configuration you are using. This is particularly relevant for this particular case. Okay, so we have a pressure outlet at the this location which I have just shown. I don't know why this keeps getting selected. Okay, anyways, so pressure boundary condition will have zero gauge pressure. It means it is at atmospheric pressure. That's all I wanted to keep it here. And then again, the turbulence you can give any. You can use the default values, or if you want, you can change it if you have data available. Okay, acoustic we are not interested in, so we'll say acoustic is off. You can also have non-reflecting, but for your purpose, off is quite okay. Temperature you can keep 300, and that's it. So two major boundary conditions: one is the inlet, one is the outlet, and other boundaries are basically walls. So this is a wall. This nozzle contour is a wall. So like that, this will be a no slip wall. That's all. There is no. It will be a stationary and no slip wall. So stationary wall, no slip, shear condition. That's all. Roughness model you can give standard, or if you have any, you want to use any fancy wall model, that you can apply. But standard for our purpose, we want to keep it. My idea was to keep it simple and just look at the effect of density. Basically, how your because of pressure changes, how your density, temperature, these things change. So for that, standard wall function is quite okay. Okay, so these are the boundary conditions. I have told you about material, model, and body condition. I think that is fine. Reference value will keep atmospheric. That's it. I have not made any changes here. So that's it. Then you can run. You can give a small time step and run for number. You give a very large number here so that it runs for some time. It basically gets converged. That is what we are trying to do here. And then you will get these results. So basically, you are interested in velocity. You can also look at your Mach number. So this is how your Mach number will vary. So these are called shock cells. I will explain it later on, but this is getting formed because the inside pressure is high. When it comes out to ambient conditions, this is how it behaves. So this is something you would expect in your the two people working on CD nozzle. So for that, once it comes out from that nozzle, if you remember the plot that we studied, let me. Okay, I will go to that later. So this is what. Any questions on this settings, or so we can look at absolute pressure, density. These are the various things that we are interested in. Okay, you can change the scale and so this is your density. You can change it to look it more clearly or something like that, or you can keep it 4.5. So these are the shock cells getting formed. Okay, let me stop recording. If you have any questions, you can